Swayam Prabha. Digital India. Educated India.
Welcome to lecture 16 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Instrumental Variable Estimation. In a multiple linear regression model, one of the basic assumption is that the exogenous variables are uncorrelated with the disturbance term. That is, if x is the matrix of observations on exogenous variables, then expectation of x transpose u is equal to 0. However, if this assumption is not satisfied, then the OLS estimator becomes biased and it is inconsistent also. So, for proving the unbiasedness of OLS estimator, we make use of this assumption. Now, in several applications, you may observe that this assumption is not satisfied. In particular, if you consider the errors in variable model, this assumption is not satisfied for those models, or even for simultaneous equation models, this assumption is not satisfied. So, in that case, if we directly apply the method of least squares, then the OLS estimator is not unbiased and it is not even consistent. So, definitely we require some alternative estimation procedure. So, the objective of this lecture is to consider such kind of problem when x is correlated with u, and then we will discuss an alternative estimation procedure, that is instrumental variable estimation procedure for estimating the vector of regression parameters. We will also study the properties of the estimator, and then we will also consider a test for testing the set of linear hypotheses based on the instrumental variable estimator. So, now we consider the model y equal to x beta plus u. Again, y is n cross 1 vector, x is n cross k matrix and u is n cross 1 vector. We will assume that u follows some distribution with mean vector 0 and variance covariance matrix sigma square u I n. In some situations, we take the distribution of u as multivariate normal distribution. Then one of the basic assumptions is that either x is non-stochastic, or even if it is stochastic, expectation of x transpose u is equal to 0. Now, suppose expectation of x transpose u is not equal to 0, means x and u are correlated with each other. Then we observe that expectation of b is equal to beta plus expectation x transpose x inverse x transpose u, and since expectation of x transpose u is not equal to 0. So, expectation of b is not equal to beta. So, b is biased estimator of beta. Again, if we consider the probability limit of n inverse x transpose u, then suppose this probability limit is also not equal to 0. That is, x and u are correlated even in limit. For n tending to infinity, x and u are correlated. In that case, the probability limit of b minus beta is equal to the probability limit of v divide x transpose x by n. So, you get n inverse x transpose x whole inverse, then we have n inverse x transpose u. Then usually we assume that n inverse x transpose x tends to a finite matrix. But what about this term? This term does not tend to 0. So, this probability limit is not equal to 0 or probability limit of B is not equal to beta. Therefore, B is a biased estimator of beta and it is even inconsistent estimator of beta. An example of model having this kind of problem because of correlation between x and u is measurement error model. We will discuss this model in details in next 2 lectures, that is lecture 17 and lecture 18. Just in brief, I will discuss this example. By measurement error, we mean imperfect measure of true variables. Now, suppose your observed study variable is y curl. So, y curl is n cross 1 vector of observations on the study variable, and then your explanatory variable is actually x curl, which is also n cross 1 vector, and that relationship is y curl equal to beta naught plus x curl beta 1. Now, suppose y curl is observed with additive measurement error, say y equal to y curl plus u, and then x curl is also unobservable. So, x be the vector of observed or proxy values of the explanatory variables related to the true x curl by x equal to x curl plus v. So, here we have y equal to y curl plus u and x equal to x curl plus v. So, x's also have some kind of error. Since the actual explanatory variable is x curl, but we cannot observe this actual explanatory variable, either it is unobservable or even if we observe it with some error, and x is the observed value. Then we can write the model as y equal to beta naught plus x curl beta 1 plus u and x is equal to x curl plus v. Then we assume that expectation of u is equal to 0, expectation of u transpose is equal to sigma square u I n, expectation of v is 0, then expectation of v transpose is equal to omega I n say, and expectation of v u transpose is 0, that is u and v are uncorrelated with each other. So, actually in this model y is generated by this system and x is generated by this system. Now, we can combine these two equations and then we obtain the model y equal to beta naught plus beta 1 x plus w, because x is the observations which we have taken as proxy of x curl. Actually, since x curl is either unobservable or it has been observed with some measurement error as x. So, we cannot estimate this model directly. So, we replace x curl by x minus v here, and so the combined or composite disturbance term is w equal to u minus v beta 2. This is the composite disturbance term. Now, this equation also looks like a simple linear regression model. So, of course, you can apply the method of least squares for estimating beta naught and beta 1, but then there is a problem. If we take expectation of x transpose w, then this is equal to expectation of x transpose, we take w equal to u minus v beta 2. Then even if we assume that expectation of x transpose u is 0, the second term does not have expectation 0. Why? Because if we write the second term as minus expectation x of x transpose v beta 1, then x is equal to x curl plus v. So, we get minus expectation x curl plus v transpose v beta 1, Again, even if x curl is uncorrelated with V, so the expectation of x curl transpose V becomes 0. V is also involved here. So, you get a term minus expectation V transpose V beta 1. Then expectation of V transpose V is not equal to 0. So, finally, expectation of x transpose W is not equal to 0. So, in this model x is correlated with W. So, if we apply OLS estimator for estimating the parameters of this model beta naught and beta 1, then the resulting estimators are biased and inconsistent, and this problem arises because of the correlation between x and W, the explanatory variable and the disturbance term. So, now we consider two examples. In the first example, we consider autoregressive model in which y t is written as alpha plus beta y t minus 1 plus u t. So, y t is a linear function of y t minus 1, or actually this y t minus 1 is the explanatory variable. So, one period lagged value of y t is the explanatory variable. Then obviously, y t is correlated with u t, but y t minus 1 is not correlated with u t. So, y t minus 1 is the explanatory variable and it is uncorrelated with u t, because ultimately y t minus 1 depends upon u t minus 1. So, it is uncorrelated with u t. Now, we write this model in deviation form. So, small y t is equal to capital Y t minus y bar. Similarly, small y t minus 1 is equal to capital Y t minus 1 minus y bar. Then from here, the OLS estimator of beta is beta hat equal to summation t equal to 2 to n y t minus 1 upon summation over t y t minus 1 square. You have simply applied the OLS procedure for estimating beta. So, beta hat is equal to summation small y t minus 1 divided by summation y t minus 1 square. And in this expression, if you write y t equal to beta y t minus 1 plus u t, then you get beta times summation u t minus 1 square divided by summation u t minus 1 square. So, you get beta here plus summation u t y t minus 1 upon summation u t minus 1 square. Now, is it an unbiased estimator of beta? If you take expectation of beta hat, this is equal to beta plus expectation of summation u t minus u t into y t minus 1 divided by summation y t minus 1 square. Now, this is not equal to beta. Remember that y t minus 1 is equal to capital Y t minus 1 minus y bar. So, although this capital Y t minus 1 is uncorrelated with u t, but y bar involves y t also. This small y t minus 1 involves capital Y bar, and capital Y bar, which is the mean of all the observations, this contains capital Y t, and capital Y t is correlated with u t. So, although capital Y t minus 1 is uncorrelated with u t, but small y t minus 1 is correlated with u t. and this makes the estimator biased. This part is not equal to 0. But the estimator is consistent, although it is biased, but it is consistent, because if you take the probability limit of beta hat, then it is equal to beta plus, in the numerator you get the covariance between y t minus 1 and u t divided by variance of y t minus 1, and this covariance is equal to 0. Y t minus 1 is uncorrelated with u t. So, beta hat is a consistent estimator of beta. Then we take one more example. We take demand supply model. Now, this model actually has two equations. Actually, this model comes under simultaneous equations model, which we will discuss in another lecture later on. But the model has two equations, one is demand equation and another is supply equation. The demand equation is q t equal to alpha plus beta p t plus u t, and then the supply equation is q t equal to gamma plus delta p t plus v t. Q t is the quantity in both the equations and p t is the price. Now, the question is p t correlated with u t or v t? Here, although p t is your exogenous variable, but the question is it correlated with u t or not? Now, we get p t and q t by solving these two equations. You just solve these two equations, you equate these two equations, obtain the value of p t and then substitute the value of p t in any of these two equations and obtain the value of q t. So, you get p t equal to gamma minus alpha upon beta minus delta plus v t minus u t upon beta minus delta. Just simply equate these two equations. And then you solve it for p t. So, you get this equation, and then you substitute this value of p t in any of these two equations and you get this expression for q t. And from here you observe that this p t is correlated with u t as well as v t. So, it is correlated with both u t and v t. So, in both the equations this p t is correlated with the disturbance term, whether you take demand equation or supply equation. Then now we look for the alternative estimation procedure. An alternative estimation procedure is instrumental variables estimation. An instrumental variable z is an additional variable used to estimate the causal effect of variable x on y. So, we take a set of variables which are correlated with the explanatory variables in the model, but uncorrelated with the composite disturbances, at least asymptotically, to ensure consistency. So, we require such kind of variables as instrumental variables, which are correlated with the explanatory variables in the model, but uncorrelated with the disturbances. We consider two different cases. The first case is number of instrumental variables is equal to the number of explanatory variables. So, suppose Z is n cross k matrix of observations on k instrumental variables Z 1, Z 2, Z k, such that the probability limit of n inverse Z transpose u is equal to 0. Means these instrumental variables are uncorrelated with the disturbance term u, at least in limit. And then we also assume that the probability limit of n inverse Z transpose x is equal to sigma z x, and this matrix is finite non-singular matrix of full rank. So, obviously, the order of Z transpose x or sigma z x is k cross K, and we assume that it is a non-singular matrix. So, naturally it is of full rank. Then the probability limit of n inverse Z transpose Z is equal to say sigma Z Z, and this is also a finite non-singular matrix. So, these are the assumptions which we take about the observations on instrumental variables. Now, if some of the x variables are uncorrelated with you, then you can use these explanatory variables as some of the columns of Z as instrumental variable. For instance, the first column of x is usually consist of all the elements equal to 1, and that column is corresponding to the interceptor, and this column does not have any measurement error, or it is at least uncorrelated with u. So, you can use the first column as one of the columns of Z, or even if you know there are some more columns of x variables which are uncorrelated with you, you can use those columns as your instrumental variables. Now, we pre-multiply the model 1 by Z transpose. So, you get Z transpose y equal to Z transpose x beta plus Z transpose u, or n inverse Z transpose y equal to n inverse Z transpose x beta plus n inverse Z transpose u. Then we take the probability limit. So, we get probability limit of n inverse Z transpose y equal to probability limit of n inverse Z transpose x beta plus probability limit of n inverse Z transpose u. Now, we solve this equation for beta. So, you obtain beta equal to, you get inverse of this matrix, inverse of probability limit of n inverse Z transpose x, then you have probability limit of n inverse Z transpose y minus probability limit of n inverse Z transpose u. Now, probability limit of this part is equal to 0. We already assumed that these instrumental variables are uncorrelated with u. So, this part has probability limit 0. Probability limit of n inverse Z transpose x is equal to sigma z x. So, you get sigma z x inverse here, and then probability limit of n inverse Z transpose y is written as sigma z y. So, beta is equal to sigma z x inverse sigma z y, and then your objective is to estimate beta. So, in the expression for beta, beta equal to sigma z x inverse sigma z y. We replace sigma z y and sigma z x by corresponding sample cross moments. So, we estimate sigma z y by n inverse Z transpose y and sigma z x by n inverse Z transpose x respectively, and then we obtain this estimator Z transpose x inverse Z transpose y, and this estimator is called the instrumental variable estimator. Now, we prove the asymptotic properties of the instrumental variable B I V. The instrumental variable estimator B I V is a consistent estimator of beta. Then the asymptotic variance covariance matrix of B I V is given by, say you take probability limit of B I V minus beta, B I V minus beta transpose equal to sigma square u upon n sigma z x sigma z z inverse sigma x z. Actually, sigma x z is equal to transpose of sigma z x. Now, to prove this result, we write B I V equal to Z transpose x inverse Z transpose, then we write y equal to x beta plus u. So, you get beta plus Z transpose x inverse Z transpose u. Now, if you take the probability limit of B I V, you get beta plus probability limit of, we divide here by n. So, you get n inverse Z transpose x, then you have 1 upon n Z transpose u here. Now, the probability limit of n inverse z transpose u is equal to 0, and the probability limit of n inverse z transpose x is sigma z x. So, you get beta plus sigma z x into 0. So, this is equal to beta. Further, the asymptotic variance covariance matrix of B I V is given by, say we write it where B I V. So, this is the asymptotic variance covariance matrix of B I V. So, this is equal to n inverse probability limit of n inverse z transpose x inverse n inverse z transpose expectation of u transpose z n inverse x transpose z inverse. Actually, we get this expression when we substitute B I V minus beta equal to z transpose x inverse z transpose u. So, B I V minus beta transpose is equal to, you take 1 upon n z transpose x inverse and then 1 upon n z transpose u transpose z, then you have 1 upon n x transpose z whole inverse. And then for taking the probability limit, we take expectation of this part and then we take limit n tending to infinity. So, you get this expression. Now, expectation of u transpose is equal to sigma square u I n. So, we take expectation of u transpose this and then we obtain this expression equal to sigma square u upon n probability limit of n inverse z transpose x inverse, then you have probability limit of n inverse z transpose z, then probability limit of n inverse x transpose z inverse, or you get sigma square u upon n. The probability limit of n inverse z transpose x is equal to sigma z x. So, you get sigma z x inverse here, then the probability limit of n inverse z transpose z is sigma z z, and then again you get sigma x z inverse. So, you get this expression. Further, we observe that as n tends to infinity, the asymptotic variance covariance matrix of B I V tends to 0 because of this factor. All other matrices are finite. So, this asymptotic variance covariance matrix tends to 0. So, B I V is a consistent estimator of beta. The probability limit of B I V is equal to beta and its asymptotic variance covariance matrix tends to 0. Hence, the result follows. Now, we consider the second case, when number of instrumental variables is more than the number of explanatory variables. So, Z is of order n cross L and L is greater than k. And then we also assume that the probability limit of n inverse Z transpose x is equal to sigma Z x, and this is a finite matrix of full rank. Then the probability limit of n inverse Z transpose u is equal to 0. That is, in limit Z is uncorrelated with u. And then the probability limit of n inverse Z transpose Z is equal to sigma Z Z. Then we write the model y equal to x beta plus u, and then we pre-multiply the model by Z transpose, and this gives you Z transpose y equal to Z transpose x beta plus Z transpose u. Then if we obtain the covariance matrix of Z transpose u, it is sigma square u Z transpose Z. Say expectation of Z transpose u, and then we take transpose of this u transpose Z is equal to Z transpose, you take expectation of u transpose. So, you get sigma square u I n Z, and then this is equal to sigma square u Z transpose Z. Then we apply GLS to model 4. So, your model 4 is Z y equal to Z x beta plus Z u. Actually, it is Z transpose y equal to Z transpose x beta plus Z transpose u, and we apply GLS to this model. So, you get beta hat equal to, here the expression is x transpose Z, then we take Z transpose Z inverse, then Z transpose x whole inverse, and then x transpose Z. Again we take transpose of this matrix, then in between we take Z transpose Z inverse, and then we have Z transpose y here. And then we write P z equal to Z, Z transpose Z inverse, Z transpose. So, we get B I V equal to x transpose P z x whole inverse x transpose P z y. So, P z is equal to Z Z transpose Z inverse Z transpose. Then again the instrumental variable estimator B I V is a constant estimator of beta, and its asymptotic variance covariance matrix is sigma square u upon n, sigma x z, sigma z z inverse, sigma z x whole inverse. Again, to prove the consistency and to derive the asymptotic variance covariance matrix of B I V, we write B I V equal to x transpose P z x inverse x transpose P z y, then we substitute y equal to x beta plus u. So, you get beta plus x transpose P z x inverse x transpose P z u. We are writing y equal to x beta plus u here. So, from here we obtain probability limit of B I V minus beta equal to the probability limit of n inverse x transpose P z x whole inverse, the probability limit of n inverse x transpose P z u. Then we substitute the value of P z here. So, we get x transpose Z, Z transpose Z inverse, Z transpose x. This is actually equal to x transpose P z x, and then we write it equal to 1 upon n x transpose Z, then you have 1 upon n Z transpose Z whole inverse, then you have 1 upon n Z transpose x, or we take 1 upon n also here. So, that you get. So, the probability limit of this part is probability limit of n inverse x transpose Z, probability limit of n inverse Z transpose Z whole inverse, probability limit of n inverse Z transpose x. Then we have the second part, n inverse x transpose P z u, 1 upon n x transpose P z u. This is equal to 1 upon n x transpose Z, then you have 1 upon n Z transpose Z inverse, then you have 1 upon n Z transpose u. So, you get this part, and then we take the probability limit. The probability limit of n inverse Z transpose u is equal to 0. So, this is equal to 0. So, this makes the entire term equal to 0. So, probability limit of B I V minus beta is equal to 0. So, B I V converges in probability to beta, but still you have to show that its asymptotic variance covariance matrix tends to 0. Now, the asymptotic variance covariance matrix of BIV is obtained as say probability limit of x transpose p z x inverse x transpose p z expectation u u transpose p z x x transpose p z x inverse. So, then you obtain sigma square u upon n, the probability limit of n inverse x transpose p z x inverse, because again the expectation of u u transpose is sigma square u I n, and then p z is an idempotent matrix. So, you get x transpose p z x here, and then finally, you obtain this expression, and then we substitute the value of p z here. So, we get sigma square u upon n, the probability limit of n inverse x transpose z, then you have probability limit of n inverse z transpose z inverse, then probability limit of n inverse z transpose x whole inverse, and then we obtain sigma square u upon n. The probability limit of this part is equal to sigma x z. Probability limit of this part is sigma z z inverse, and the probability limit of this part is sigma z x, and then you have whole inverse. Then as n tends to infinity, the asymptotic variance covariance matrix tends to 0 because of this factor. Thus, BIV is a consistent estimator of beta. Now, we consider interpretation of BIV estimator as a two-stage least squares estimator. So, we consider the regression between x and z. So, x is equal to z b plus w, and then we apply OLS procedure here. So, the OLS estimator of B is B hat equal to z transpose z inverse z transpose x. Then we obtain a matrix of fitted values of x. Say x hat equal to z b hat, and then we substitute the value of b hat here. So, you get x hat equal to z z transpose z inverse z transpose x, which is equal to p z x. Then in the next stage, we run regression between y and x hat to get the two-stage least squares estimator. So, you get p say 2 SLS equal to x hat transpose x hat inverse x hat transpose y. Now, x hat is equal to p z x. So, x hat transpose x hat is equal to x transpose p z x. So, you get this, and then x hat transpose y, again x hat transpose is x transpose p z y, which is the same as the instrumental variable estimator. So, this is another interpretation of the instrumental variable estimator as a two-stage least square estimator. First, we run the regression between x and z, then we obtain the fitted value of x, and then we run the regression between y and fitted value of x, and finally, we obtain a consistent estimator for beta. So, we have this step, we obtain x hat equal to p z x, and then run regression between y and x hat. So, from this two-stage procedure, it becomes clear what this instrumental variable technique does. So, this instrumental variable technique allows the use of only that part of the variation in the predictor x that is not related with unobservable factors contained in u, affecting both predictor and outcome. So, you can say this x has two parts, and one part is related with u, unobservable factors involved in u. So, this x hat, which is equal to p z x, This in some sense you can say extracts that part of variation in the predictor variable x, which we are using in our regression and which is not related with u. Or you can say this method allows to estimate the causal relationship between the outcome y and the predictor x. Then the instrumental variable actually affects y only through its effect on x. It is not related with y directly, it affects y only through x. So, suppose you want to investigate the relationship between depression and smoking, how much depression a person has and how much he smokes. Then suppose lack of job opportunities is your variable z, and all these variables are say measurable. Now, lack of job opportunities could lead to depression. So, z is related with x, but it is only associated with smoking through its association with depression. So, there is no direct link between z and y. There is no direct link between lack of job opportunities and smoking, but still you are finding some correlation between z and y, but it is just only through x. So, z can be used as an instrumental variable, or you can say suppose you have this kind of situation. Say z is related with x, x and y are also related with each other. Then why we face the problem? Because x is related with u also. There is correlation between x and u. So, that is why your OLS estimator fails to provide you a consistent estimator. Then of course, there is a link between y and u also. Now, suppose z has link with u, then you cannot use z as an instrumental variable, or if z also has direct link with y, still you cannot use z as an instrumental variable. But if z is related with y through its link with x, z has link with x, x has link with y, then you can use z as an instrumental variable. Choice of instrumental variables. Of course, we cannot use the actual data to find instrumental variables. It is very difficult to distinguish between different situations, which just we have discussed on the basis of data. You do not have any testing procedure to test whether the z has link with y only through x. So, one has to rely on knowledge about the model's structure and say the economic theory behind the experiment, or whatever theory is there behind the experiment. So, you have to rely on that, and then accordingly based on your knowledge you have to select a proper instrumental variable. But you have to take care that z should not be affected by other variables in the system. It should not be affected by y directly, that is, and then z should be uncorrelated with u also. So, covariance between z and u should be equal to 0, but z should be correlated with x, that is covariance between z and x is not equal to 0. Then weak correlations lead to misleading estimates for parameters and standard errors. Now, if some of the x variables are uncorrelated with you and used in instrument, then you can use those variables as instruments, and then in that case we partition x and z as say x equal to x 1 x 2, z equal to x 1 z 2. So, we are using this part of x as instrumental variable also. So, suppose x 1 is n cross r is less than k, which is uncorrelated with u, x 2 is n cross k minus r, which is correlated with u, and z 2 is n cross l minus r. These are the instrumental variables. Then x hat is equal to say x 1, x 2 hat. X 1 is the instruments for themselves and x 2 hat is equal to z, z transpose z inverse, z transpose x 2. These are the remaining regressions. So, you have x 1 and x 2 hat, and then you can apply the usual instrumental variables estimation procedure for estimating beta. Then how many instrumental variables to use? So, minimum number is k. So, L should be greater than or equal to k. Then the asymptotic efficiency increases, but with L, but finite sample bias also increases. So, suppose for example, if we take L equal to n, then what is P z? P z equal to z, z transpose z inverse, z transpose. Now, L is equal to n. So, z is of order n cross n. So, you can write it as z, z inverse, z transpose inverse, z transpose. So, this is equal to I n, and in that case B I v is equal to x transpose x inverse x transpose y, because P z becomes identity matrix. So, B I v is equal to B, the OLS estimator. Now, this is a biased estimator. Now, this is the extreme case. You have L equal to n, and then B is the biased estimator. So, if we increase the number of instrumental variables, the finite sample bias also increases. Further, well, I have not proved this result, but mth moment of instrumental variable estimator exists if m is less than L minus k plus 1. So, if L is equal to k, even the mean does not exist. That is why we have not considered the bias part here. We have just studied the asymptotic properties of the instrumental variable estimator, and with one more instrument mean exists, but variance does not exist. Now, we consider the test of linear restrictions. So, we consider the model y equal to x beta plus u. Again, x and u are correlated with each other, and you have to test the hypothesis H naught r beta equal to small r. Again, this capital R is of order q cross k, and this has rank q, and then small r is of order q cross 1, and the alternative hypothesis is not H naught. Then after first stage of regression, you get x hat equal to p z x, and then these are the steps of the test. First, we regress y on x hat with restrictions, means you consider the regression between y and x hat. So, you take w. So, you take the restriction r beta equal to small r and run the restricted regression, and then we obtained restricted regression estimator say B R S, and then we calculate the residuals E R, which is equal to y minus x hat B R S. Then in the next step, we regress y on x hat without restrictions. So, we simply obtain B u r equal to x hat transpose x hat inverse x hat transpose y, and then again we obtain the residual E u r, which is equal to y minus x hat B u r. So, we compute these residuals E. Now, we can calculate the F statistic for H naught, which is F equal to E r transpose E r minus E u r transpose E u r, and then we divide it by the number of restrictions q divided by E transpose E upon n minus k. Now, under H naught, that is under the hypothesis H naught r beta equal to small r, the asymptotic distribution of this statistic is F distribution with q and n minus k degrees of freedoms. So, using this asymptotic distribution, you can easily form the critical region for this hypothesis. So, suppose this is your calculated value of f. So, suppose we denote it by f calculated, then we reject H naught if f calculated is greater than say f. Say suppose you are using alpha level of significance, then you have alpha q n minus k. You get this value from the f table, or you can write here. So, you can even use the technique of instrumental variables for testing the set of linear hypothesis r beta equal to small r. So, in multiple linear regression models, if one of the assumptions in the multiple linear regression models, if the assumption that exogenous variables are uncorrelated with the disturbance term, that is x and u are uncorrelated with each other, is not satisfied, then the ordinary least square estimator of beta is biased. Practical situations, in particular we face this kind of problem in measurement error models, or we also face this kind of problem in simultaneous equations models. Then one of the alternative estimation procedure is instrumental variable estimation procedure, which we have discussed in this lecture. We also studied the properties of the instrumental variable estimator. It is consistent, and a big problem is the selection of instrumental variables. You have to select the instrumental variables in such a manner that instrumental variables are correlated with x, but uncorrelated with u. Then the instrumental variables are not directly correlated with y. The instrumental variables are correlated with y only through x's, and instrumental variables are uncorrelated with the unobservable factors contained in u. So, this is a big problem, but one must be careful about selecting the instrumental variables, keeping these things in mind. Say in the next lecture, I am going to discuss the errors in variables model. In errors in variables models also we face the same problem. The explanatory variables are correlated with the disturbance term, and then we face the problem of inconsistent estimators. So, we will discuss those models in the next lecture. Here I am going to stop. So, thank you.
Many a times we all think, who am I? Why am I doing whatever I am doing? Why do I feel attracted towards others? Why do I feel very aggressive in certain instances? Why certain people or certain type of acts they repel me? Why is it that I always search for certain things which look very, very ambiguous? These are the things, these are the questions that all of us experience, all human beings. And you would realize that many a times certain domains of knowledge, especially within social sciences and all sciences at large, when you look at it from a philosophical point of view, they would try to give you the answers to these questions. Now, one of the branches of understanding which helps you understand things much better, which also helps you understand not only what is visibly present before you, what is glaringly apparent to you, rather which also tells you what is not visible at all, what goes within. Okay. And this is the subject knowledge what is called as psychology. It is not only that it helps you understand the manifested behavior, the overt behavior, how you talk, how you speak, how you say it, how you interact, how you respond, not only that, but also what goes within, what makes you do this, what makes you think this way, what makes you act that way. Why is it that certain things you appreciate, certain things you feel attracted towards, and why is it that many a times in certain type of situations you feel you should completely go out of it, you should not get anyway involved into it, the repulsion. Why is it that certain acts, although you do not appreciate, still you get involved into it? Then you reinterpret your own behavior and you start giving birth to certain type of experiences, shame, guilt, pleasure, appreciation. You see world in a particular way, you analyze it in a particular way, you derive emotion out of it, feeling out of it, and the mix of what you perceived along with what you experience, it makes you act in a particular way, respond in a particular way. Your response is received by somebody else, and then the other person also responds in that situation. Now, there are situations where several people interact simultaneously, the situation remains constant and different people interact at the same time. You realize that your identity gets lost. You are not an individual, you act what is called as group behavior. You realize that you do not have an explanation for either favoring somebody or completely being unfavorable to the other person. You later on realize that it was a favorable or an unfavorable attitude towards that individual. You realize that you repeat certain form of behavior. Why? You do not know. People tell you that such type of repetitions are not normal. Human beings largely do not do that. And then you realize that okay, this is a particular pattern of a behavior for which I require the help of a specialist. The specialist tells me that this pattern of behavior is given a particular taxonomy, a particular nomenclature, which is either some aberration in the normal behavior, it is a neurotic form of a behavior, psychotic form of a behavior, it could be a psychosomatic response. And psychology, it covers all of this. So, if you want to understand yourself, if you want to understand others, this is the subject which helps you achieve that target. It is behavioral sciences that makes you understand human beings, human responses, human existence in complete totality.